Substituent effects in electrophilic aromatic substitution. So far, we have been talking about the reaction between benzene and an electrophile. If you notice in the acylation, we just had a benzene react with the acyl group. There was nothing on benzene. I'm talking about in terms of substituents like a nitro group, NO2, a bromo group, halogen, a methyl group, etc. None of those were attached to the benzene ring. The moment you attach or you have a benzene with a substituent on it, the chemistry is profoundly different. What do I mean by that? So here is an example. If you were to react phenol, this is phenol, with nitric acid at 20 degrees Celsius, you would get, so you would say, okay, well, I can add the nitro group anywhere I want, but no, you can't. The answer is you can only add it to the para and ortho positions only. So you only get ortho and para. You don't get the meta position. And the moment you now have a nitrobenzene and add nitric acid to it, you would need incredibly harsh conditions. You would need sulfuric acid at 100 degrees Celsius. And then you would get the nitro at the meta only position. If you needed harsh conditions, it means your aromatic compound was not that reactive. So it turns out that this is much more reactive. That's why we needed room temperature, and this one was less reactive. And you resorted to harsh conditions using strong acid and 100 degrees Celsius, which is high for organic reactions. Very well. Let's look at then what's happening here. There must be something happening that's causing these conditions to change. So then we get into the idea of having electron donating and electron withdrawing groups. We already discussed them in chapter 16, but now we're going to discuss them more in depth. So it says here that a group that is already present on a benzene ring may make it easier or harder to introduce new substituents and can direct where the new substituents will go. So these, whatever you add from here to the benzene ring with whatever substituents is attached, depends on how the substituents react to that incoming substituent, meaning the OH here decides where the NO2 is going to go. The same thing here, the NO2 decided where the other NO2 that's coming from the nitric acid is going to go. So that's what we say by directing. So they direct where the new substituents is going to go. So let's begin with the two types. We have what we call ring activating groups or substituents. And this is a group that makes it easier to introduce new substituents in ring activating. And the ring activating substituents are electron donating. So there are EDGs. And why is that the case? For a very simple reason, is that they make benzene, electron rich, which is more reactive. If your benzene ring is very, very stable, it's not going to react. But if you make it rich, just like you did with the diene before, where you added electron donating groups, then the reaction is going to take place much, much faster. Well, let's look at electron donating groups. As we discussed in chapter 16, there's something common about the majority of them. Let's begin with the first ones. So first of all, if you have an oxygen with a negative charge on it, all the way to OR, these are considered strongly activating. Let me make this a bit clear here. These are strongly activating, and I will show you on the handout that all of this is actually nicely laid out. Toward the end, you have weakly activating groups. So this is an alkyl group and then aryl group, which is basically a benzene ring with another substituent on that benzene ring. All of these two are considered weakly activating. In the middle, they tend to be moderately activating. Let's begin with the strongly activating. What's so different about them? If you take a look, there's something about them is that they have lone pairs on them. Here's a lone pair. They have lone pairs. So that's why they're electron donating. And of course, this can be a methyl, etc. Just giving you an example. So it turns out that having one of these on your benzene ring will increase the rate of your reaction compared to benzene, where you have just an H attached. So they're all better than having no substituent. Again, something to say here is that all of them except weakly activating groups have lone pairs. All have lone pairs except weakly activating. So no wonder why OH has its lone pairs. So it's an electron donating group, plus it's also a strongly activating group. It made the benzene ring more reactive, but of course it directed it to an ortho pair. We'll get to that in a second. The other type is ring deactivating. So those are deactivating groups. And this is a group that makes it harder to introduce a second substituent, is ring deactivating. So it deactivates the group. It doesn't make it as reactive. And the ring deactivating substituents are electron withdrawing groups. So EWG. You are familiar with these. So what do they do to the ring is the benzene, they make the benzene less reactive. So they make benzene less reactive. And not as electron rich. Very well. So let's take a look at these electron withdrawing groups. So they begin with NO2, the nitro group. And if you look at nitro, if you draw it out, it looks like this. Use a different color for this. This is delta positive. Well, actually, it has a formal charge, but it's also delta positive. So we'll just put the full charge on this. If you calculate the formal charge. So these are electron withdrawing groups because they're already suffering from some a lack of electron density. If you look at nitrogen right here, and those electrons on the oxygen are, or the electronegativity of oxygen is withdrawing electrons toward itself. So here they are. Where are your strongly deactivating groups? There's also something common about them is they have either a full positive or a partial positive. So again, this has a full positive on it. We showed it here. And R3 has, or the amines, protonated amines or quaternary amines, meaning they have 4 bonds on nitrogen. So here I'll show that to you. That's basically nitrogen with 4 bonds, whether they are R groups or H's. I'm just showing you, for example, this one right here. So you see the positive on it, or they have a delta positive, because they have electronegative atoms, etc. Delta positive. Very well. So all of these, all the way there, those are strongly deactivating. Once again, let me write this down. All have partial positive or full positive charge on atom directly attached to benzene. So instead of giving benzene electron density, they're taking away electron density from benzene. That's why the benzene is less reactive. Very well. So let's show you something here. This sheet is available on Brightspace, and you can use it. This one has them listed for you. It's called the activating and deactivating benzene groups. So you have the most activating all the way down to the most deactivating. And if you notice there, these are EDGs, electron donating groups. They're activating, and of course, they are listed or classified by whether they are strongly activating, moderately, or weakly activating. As well as your reference is the H, because there's no, again, there's no substituent, it's just an H. And again, you have the moderately deactivating. So this one is even more extensive than what you have in the, and I say in your notes: ketones, aldehydes, amides, esters, and carboxylic acids. And then the strongly deactivating are right here. Okay. So there's also something we're going to explore in the next few pages, is that where do they direct? They direct toward ortho para. Those are the activating, and then the meta are where the deactivating groups. So we'll have to explain this, and there's a theory behind it, and we're going to go there next.